Good morning, ladies and gentlemen. I have a good one for you today. This is another episode of Dave Does Math from Home, and this is one of my favorite pieces of calculus. This is where calculus gets really interesting. We're doing section 3.11, which is related rates. So, before we get into this, I just want to give you all the disclaimer. Related rates is a really fancy way of saying implicit differentiation story problems. So this is going to be a challenge. This is one of the sections in mathematics that students consistently struggle with the most. I don't want to scare you, I just want to warn you, it's going to take some getting used to. In this section, we are going to take situations, word problems, that describe things that are moving or changing. We're going to represent those story problems using functions that model that movement or that change. We're going to use implicit differentiation to find the derivatives of those functions, and then we'll use that to look at how these things are changing. And the only really good way to get into this is just throw yourselves into it. So let's begin with a cool story problem. My favorite involves spheres. A spherical balloon is inflating at a rate of, we'll say, 3 cubic centimeters per second. That seems like a reasonable rate for a balloon to be inflating. How fast is the radius changing when the radius is 10 centimeters? And then later, 20 centimeters. So this is two questions. It's one situation. The spherical balloon is inflating at a constant rate. There are two questions here. How fast is the radius changing when the radius is 10 centimeters? It's pretty small. And how fast is the radius changing when the radius is 20 centimeters? A little bigger. The interesting thing about this question and the way that it's being posed right now is that most students will guess that these rates should be the same. If it's inflating at a constant rate, it's very easy to assume that the radius will also be changing at a constant rate. So however fast the radius is changing when it's 10 centimeters, you think should be how fast the radius is changing when it's 20 centimeters, or when it's 80, or when it's 100, or you think that this size shouldn't really matter. And that's not true. That is not how this situation works. If you think about a small balloon, when it's 10 centimeters in radius, you've got a balloon about this big. In 1 second, you're adding 3 cubic centimeters to that, and that 3 cubic centimeters is going to stretch out the outside of this balloon. So you're basically, you can think of it as like creating a shell around this sphere. And that shell, that increase in volume that is all going on the outside, the difference between your 10 centimeter balloon and how big it is when you add 3 cubic centimeters of air to it, that difference, that 3 cubic centimeters, is going to be distributed around the outside of this 10 centimeter radius sphere, and it'll add a certain amount of thickness. That's the radius that you're adding. If you do that to a 20 centimeter radius balloon, that 3 centimeters is going to be stretched much more thinly across a lot more surface area, and it's going to create a much smaller impact, a much smaller change in radius than when the balloon was smaller. Small balloons, you add 3 cubic centimeters, they get proportionally bigger than if you take a bigger balloon and add 3 centimeters of volume. So that's what we're looking at here. We're exploring that relationship with calculus. That's the theoretical description of what's going on. The calculus, here's how to do it, explanation starts now. We have to start with a formula, an equation that we can use. We're looking at spherical balloons. So we want the volume of a sphere, and so that's going to be important. The volume of a sphere, I know how to spell sphere. Give me a second. I can do this. The volume of a sphere is 4/3 pi r cubed. This function gives us the relationship between the radius and the volume, which is great. We need that. What we need more is the relationship between the change in volume and the change in radius. So for that, we need derivatives. Derivatives, we know that fundamentally derivatives are all about rates of change. That's what the derivative means. It gives you a slope, a rate of change. So we're going to take these measurements, we're going to take a derivative of this whole thing using implicit differentiation to get a new function that tells us the relationship between these rates, like this. Related rates. We're looking at the relationship between the rates. So let's just take a derivative. The derivative of volume should be dV. The derivative of this, 4/3 and pi are just coefficients. Those are safe. I'm not going to worry about those. The derivative of r cubed is 3r squared dr. Now I have a function that is about the rate of change of volume and the rate of change of radius. And now these things are connected. They weren't before. This was just about the volume and the radius. This is about the rates of change of those things and how they're related. This is what I can use. You can also cancel the 3's if you like, if you want to simplify this. Once I have this, I need to actually look at my problem and see what's being given. The spherical balloon is inflating at a rate of 3 cubic centimeters per second. This is a rate of change of volume. So that's going to be dV. dV equals 3 cubic centimeters per second. How fast is the radius changing? That means that dr, the rate of change of radius, is the question. This is what I need to solve for. This is what I need to find. When the radius is 10 centimeters, r equals 10. So this is given, I'll do the r equals 20 version later. So, start with a function that relates quantities. Use implicit differentiation to create a function that connects rates. Plug in some numbers, solve for what's missing. dV is 3. These 3's cancel, so 4 pi, r is 10. 10 squared times dr, r is unknown. So this thing is going to simplify into 400 pi. So dr equals 3 over 400 pi. It's not much. It's a very, very small amount. I guess it's centimeters. No, centimeters per second. That's what it should be. I left the units off because I'm bad at this. This is 3 cubic centimeters per second. These are unitless. This is centimeters. So yeah, cubic centimeters per second got divided by centimeters squared, which leaves us with centimeters per second. Yeah, which makes sense. The change in radius is measured in centimeters. Change in radius should be centimeters per second. So 3 over 400 pi centimeters per second is how fast the radius changes when the radius is 10 centimeters. If we do this again when the radius is 20 centimeters, we can use our same related rates equation here. dV is still 3 cubic centimeters per second. 4 pi are unitless. R is now 20 centimeters. And dr is still unknown. So 20 centimeters squared would give us 400 square centimeters. Times this 4 will give us 1600 pi. So 3 centimeters cubed per second divided by 1600 pi centimeters squared should give us dr equals 3 over 1600 pi centimeters per second. And that's it. Looks bad, but it's really just about identifying the relationship, use implicit differentiation to take a derivative of that, keep your dVs and your dRs or all the different pieces there. Identify what pieces from the problem are giving you what pieces of information. Some of them will be rates, some of them will be quantities. Plug all of that in and solve for what's unknown to answer the question. That's related rates. I will do another example on a separate video. I don't think I can finish before the camera cuts me off.